please put in their name and their email into the raffle box. Speak now or forever hold your peace. Miss Lillian Chan, can you please pick our first winner for the day? I put my name in here 3 times, so. It's blank. Who's blank? Oh, yes. Of course. Yvonne Tang. Yay! Woo! And we'll pick one more. Let's pick one more. Women pick women, you know. And she picks Ryan Barry. Come on up. You get your choice. And not only that, there's even beautiful little notebooks, like for block paper. Block paper, guys. Check it out. Pick one. Effect in modern C++. Sure. Cool. And we'll do another one after lunch. So, thanks for cleaning up after yourselves, you guys. Next time, if you want to bring a cup or a mug or a thing, that also saves these beautiful styrofoam cups. We'll have some awesome pizza at around 12:15 or so. So it'll be a couple slices for pizza and 1 soda per person. You know, we're the Army here, right? So with that, I'd like to introduce to you Srinivasan Sriram. So Sriram will, one of the co-producers of the course.
Thanks, Robert. Hi, folks. Thank you for all coming. We had a massive, over 105 people who actually applied for this, and approximately 34, 33, or some such number is what you see in the room right now. For those of you who weren't here the other day, we're trying to sort of make this the locus of all things blockchain in the Valley. We're calling it the Consensus HQ. We being Tom Ding of Coinify and myself of SkewChain. And the goal is really, to get more people excited about what we think is very disruptive. There's a lot of interesting people in the room right now, and I'm sure over time there'll be projects and stuff that'll come out of this. There are serial entrepreneurs, there are lawyers, of course, engineers. So, to the extent that all of us here can help you guys get your projects off the ground, nothing like it. We're also a small startup ourselves. We've been around only for 3.5 months, so we don't have a whole lot of cash. We can't really afford massive amounts of lunch every day, so we're trying to find sponsors. If you know someone, if your companies want to sponsor a lunch, please feel free to, ping Robert. Any questions? Just ask any one of us here, and that's it. Thank you for coming.
Thanks, Sriram. So that's SKU Chain, and Tom Ding's Coinify with a K. And Tom Kaiser is here from Coinify in the back, so you want to talk to him about anything Coinify? And then Tom Ding will probably be here next week, if not later today. So with that, I'd like to bring up Atif Nazir of Block.io. He's CEO and founder of Block.io. Let's give a big hand for our next instructor, Atif Nazir.
Thanks, Robert. Sure. Can you guys hear me in the back? Yeah. If I hold it like this, you can. I'll try to take this from where Ryan left, and I'm just going to log in for some interactive demos if we have to do that. What are public keys? In elliptic curve cryptography, we come up with something called a generator point. That generator point is as soon as you multiply your private key, which is a pretty large integer, with the generator point G, the result is a public representation. And the idea is you can't exactly go back to the private key. The reason for that is this multiplication that I just talked about, it's not really multiplication. We just call it multiplication because it's easier to relate to. Okay? So this curve generator point, it's known to everyone that is using the Bitcoin protocol. The way you generate a public key is you multiply the private key with this generator point G. But you can't just divide the public key with the generator point and come up with a private key. That's not going to happen. And that is because this multiplication is not really multiplication. Okay? You can go into the depth of this. There's elliptic cryptography math that you can just look at. If you are used to using Python, you can look at Vitalik Buterin's code. It's really easy to read. It's called PyBitcoin Tools on GitHub, and you can go in and see what the multiplication and the addition functions are for elliptic cryptography. It's really easy to understand, and that's something you got to give Vitalik credit for that. Any questions so far? If there are no questions, I'll assume you're lost. Yeah.
How difficult it is to reverse this, like you said, in terms of difficulty, how difficult it is to reverse this process?
It is, so the question is how difficult is it to reverse this equation and come up with the private key from the public key? It is as hard as brute forcing 2 to the power 256. 2 to the power 256, 1 quintillion integers. It's almost as hard as finding that, but not quite, but almost that. It's really hard. Given today's computers, you will need to use almost all the energy that exists in our solar system, and perhaps the universe, not the universe, our solar system, to come up with, try to reverse this public key into a private key. Now, what you want to do is, if you actually want to reverse the public key to a private key, is just hack into Bitstamp or something else, and that's the private key is stored in the database. So you can just do it. That's a lot easier than spending your entire life chasing something. Now, you might get lucky, and that is something that has actually occurred a couple of times in the Bitcoin world, that 2 different people using 2 honest code generators came up with the same integer. It has occurred, but the probability of that happening again is super small. And the reason for that is you are trying to find one atom in 1.3% of all atoms that exist. Right? Any other questions? Yes?
We just don't know if there's no reverse function. There's no published bit.
Yes.
Because governments might have a way and we don't know about it, right?
It's true.
We definitely do.
That's wrong.
Yeah.
You can prove that.
Well,
So
we don't know who Satoshi is.
Yeah.
There you go. Yeah. This is our Bitcoin right now.
There will be other problems with Bitcoin, but I think the hash function is probably not one of them.
Well, there are a lot of people that dedicate their lives to this stuff. So
Well,
we're going to wait for their updates.
You don't know whether P equals NP either. So I don't know that we're getting a little bit esoteric here. But my understanding, I'm supposed to be the guy that's keeping on track here, but I thought that my understanding is the hash functions are pretty. I mean, there's some of these hash functions that are fairly. You can trust them quite a bit. Is that what I was hearing over there?
Well, I mean, so I think the community that produced the hash functions, they're a very independent community. They're not, and especially after everything that came out last year about governments trying to compromise some of these standards and stuff like that, they're very carefully reviewing all this stuff. So they did say, for example, some of the algorithms that were favored had problems and stuff like that. So it's just that I think that community is sort of very independent and something that you can rely on. So I think, that's about all we can say. I think,
I'll wait for a paper before I come to a conclusion. But yes, people do find flaws in existing implementations all the time. We just don't see one happening soon. Yes?
You said that it's always easy, or there are other ways to kind of find out the string which was used to generate the private key. Like,
If you're typing it by yourself, we as humans are susceptible to patterns. So if I were to write a brute forcer, you can come up with the same pattern and you can come up with a private key, and then I'll make hell. I'll raise hell saying, oh my god, brainwallet.org is bad. Well, you typed a predictable password, so That's what happened. Someone else came up with the same thing.
So what is there like a standard algorithm to generate the initial key to then generate the private key?
So the question is there a standard way to come up with a private key for Bitcoin? That is basically what CSPRNGs do. Secure pseudo-random number generators, right? You can look them up, and keep in mind there are pseudo-random number generators. So for example, the OpenSSL generator that was being used until I think late May or July, that random number generator itself was pretty weak. So if you were doing transactions like 200,000 transactions from the same address, you were somehow leaking the private keys sometimes. So we'll talk about that at a later time. But that's a very interesting topic. CSPRNGs, keep in mind, our random number generators are not exactly random number generators. They are pseudo-random number generators. So if we can come up with ways to increase the entropy for randomness, so for example, quantum, there are these devices that try to do it through quantum mechanics. I don't know how successful they are, but they do exist. So this is a field to improve upon, the randomness. But if we are able to come up with something completely random, these things hold. All right, so how do we go from a private key to a Bitcoin address? This will again get a little bit complicated, but stay with me. So the private key is what we generated on that website. You know, there was a hash function of what we typed in. And through the ECDSA ECC sec P256K1 curve that we just talked about, you come up with this public key. This public key is a representation of that private key. It is really hard for me to go back from this public key to the private key, okay? So you're coming to this point. Now what you want to do is you want to create an address that mitigates some of the human error that we can introduce when we try to enter addresses on, for example, blockchain explorers, or try to send them coins and so on. So the way we do that is we pass it through a couple of hash functions. One is SHA-256, the other is write-MD160. You come up with a 160-bit string over here. Now how do you make sure that the address that you're typing, if you make a couple of errors in that address, I don't want the coins to go to it, and I want the Bitcoin protocol to recognize that this is a completely invalid address. This is how we remove some possibility of human error when we type addresses. We do that through a checksum. How do we get a checksum? Well, we apply a couple of hash functions to it. SHA-256. Message integrity, right? 4 bytes you append to this 160-bit result, and then you pass it through a conversion function called base 58. You're basically converting a base 16 string into a base 58 string, and you're giving it a certain alphabet. You're telling it you can use the letters A, B, C, D, but you can't use L because L is similar to I. But it has to be a capital I, it can't be a small l. Again, you're trying to remove human error from the entire thing, right? Not completely, but you're helping them a lot more than entering this thing, right? And the end result is a Bitcoin address. So if I go to a block explorer and I type this address, it's going to say this address was something new. Hopefully I created something random, so by chance. And this is an address that exists. It's a valid address, but there are no coins in it. And if there were, I could steal them because I like doing that. So let's do another exercise. Let's take this address and change a few things in it. So for example, this U, let's make that a P. Looks like a valid Bitcoin address, right? Starts with a 1, goes all the way. All I did was make one mistake. Let's try and enter that. Well, that's not a valid address, right? So don't be scared when you're sending coins of making a couple of mistakes. The checksum will take care of it. And that is because of the properties of cryptographic hash functions that we discussed. Very important to understand. I did not know this until I really got into it, because it was so scary trying to send money on the Bitcoin network. Oh my God, what if I change a couple of letters? Oh, my 200 Bitcoin's gone. This is very reassuring, at least it was for me. So, again, what are you doing when you convert a private key into a Bitcoin address? You are converting the private key into a public key. You are passing it through a few hash functions, and combined we basically call them base 58 check encoding, because you're converting it to base 58 and you're encoding a checksum into the address, and the end result is a Bitcoin address. And this is something other people will recognize. But what really is an address? It is basically a public key. It's a formatted version of a public key. So if you go to, for example, Litecoin or Dogecoin or even Stellar and Ripple, they're basically using a different cryptography. Stellar and Ripple are using a different cryptographic curve, but they're basically doing the same thing. The idea is the same. They're just using a different curve to do the math on. Right? Dogecoin is using the same thing, Litecoin is using the same thing as Bitcoin. Yes?
So the first time when you went and looked up that address, that random, you just typed random stuff on that Brain wallet and then you looked it up.
Yeah.
And it found something.
Yes, because
randomly, there was an address there for you.
Yeah.
And
So
that was completely random.
yes, exactly. The idea is, so the question is, I typed in something randomly on Brain Wallet, and then I looked up the address, and it was there. It was a valid address. How did that happen? Well, that happened because I basically created a random, integer in the Brain Wallet, and I converted it into a valid Bitcoin address. I went through the motions, and those motions are predefined in a manual, which is basically the Bitcoin source code, and I came up to a result that was recognized by the Bitcoin protocol as a valid result. You can do the same thing with the integer 1, for example, with the integer 2, with the integer 3, or with the string, I'm a little teapot, right? You can convert anything you want into a Bitcoin address. And this is why you don't need to go through a network or be connected to a network to create a Bitcoin address. You can do that anywhere you want. It's just that when you want to broadcast transactions, you need to be connected to a network. Okay, does that clarify things? You can take any integer and convert that into a Bitcoin address.
No one owned that. That address you
No.
just ran. Okay.
Yep.
That was I was confused.
There are 1 quintillion possible Bitcoin private keys. Okay? Yes?
The network doesn't know about that address. It's just saying the address is valid.
Oh.
You could send some coin to it, and then once you send some coin to it, then that would be blockchain, and then anyone can see it.
So that one didn't have any, but let's say you changed the private key a little bit, and then you just ended up with an address that did have something in there.
Yeah, it is possible. It has happened once or twice in Bitcoin's history.
Okay.
Not to say that is insecure, it's just the probability of that happening is really small. So imagine, it's really hard for us to imagine really large numbers, but imagine a bookshelf in which books existed, and that bookshelf covered the entire solar system. Okay? When you go and try to look up an address, you are basically pulling up one book from that shelf. How long is it going to take you to go through the entire shelf that covers the entire solar system?
Right.
It's
Yeah.
going to take you a while, and you need an elixir of whatever, like something.
But if I'm not looking for one, okay, if I'm looking for your wallet, now I need to find out.
Yeah, you just go to my database.
Then it would take forever, but what if I'm just looking for any address at all that even has 0.01?
Yeah,
Then
still
number
pretty
is-
hard. Still pretty hard.
They can do that.
People try to do that though.
Password.
That's first I heard that. So in the instance that you came upon an address that has been used already, do you get notified in any manner?
So the question is, when you come up with a private key that is already being used, do you get a notification? No. No, we build services to do that. But no, you don't get notified. You get notified in the sense that, hey, your coins are gone. and that happens to people.
So there are services that will check the entire blockchain and make sure it doesn't already exist.
Yeah, it's not as hard as it sounds. It's pretty simple.
also watch on the wallet.
So you said that the main difference between Ripple and Bitcoin is that they use a different elliptic curve.
Bitcoin and Ripple, yes.
But then,
No, I'm not talking about the blockchain. I'm just talking about the cryptography part of it. So there, like Ryan said, I haven't actually looked very deeply into Stellar, but I know that their cryptographic, the curve that they're using is different from Bitcoin's. That's all I know about it. When Ryan says that they are not actually using the blockchain, I have to defer to Ryan. He's actually looked into it, I guess.
They have the concept of distributed ledgers.
Stellar? They have something other than Bitcoin, right? Stellar and Ripple have something other than Bitcoin. What I was alluding to was they use a different cryptographic hash function, which elliptic curve. Bitcoin uses sec-p2p6k1. They use something else. I think it's a sec-2p6 R1. It's a different function.
Can you go back to a slide on where you walk through getting to a Bitcoin address?
Sure.
So here
the
on
second
the first
half
part,
of this
how you
session,
that,
we'll have more discussion on Ripple's stuff. And
on the
vitality
private
we
key
talked
part,
about will also be done in there.
the different wallets, they use different secret random generator to generate the private key.
Yes.
And there's no standard on that. That's like whatever secret random generator you think is.
The question is, can anyone come up with a private key? Yes, anyone can come up with a private key. All right, let's move forward. So I guess we went through the discussion. Let's move forward. This is stepping on the next lecture's territory, but we want to talk about what transactions are. And Ryan already talked about some of this stuff. We're just going to revisit this right now. What are transactions? If someone were to ask you, tell me what a transaction is. I know what a block is. Blocks are batches of transactions that are confirmed by miners. But what really is a transaction? A transaction is a set of instructions that you give the computer saying, move coins from location A to location B. That location B can be another person, it could be another address of yours, it could be the same address. All you're saying is move coins from A to B given a set of instructions, right? So in a typical Bitcoin transactions, what I'm saying is move coins from me to Shri, but make sure that only Shri can spend it. I can also make it so that anyone can spend it, and there are competitions that try to do that. So for example, they will ask you stuff like, what is 1 plus 1? And if the answer is 2, you can do that through the Bitcoin protocol. Anyone that has the answer to that can spend those coins. So we're basically saying, move coins from A to B, and if anyone has an answer to this question that I'm posing, they can spend these coins. Does that simplify the idea of a transaction? That's really what Bitcoin is at its core. It is a network that makes sure coins cannot be double spent, and it is a framework that allows you to give instructions to the computer and make sure those instructions are executed when the coins are spent. Yes?
So if I need to find out if somebody needs to validate how much balance I have, they need to go through all the set of transactions to come up with, might find out like each time or how?
Right, so the question is, if you want to look up the balance in an address, do you need to go through the entire transaction history to get to that balance? The answer is yes, you need to. You need to check which transactions have the coins been spent from and which transactions the coins have not been spent from.
And does that also mean I have to go through all the entire blockchain?
Yeah, so before we move forward with that, I just want to highlight what a transaction really is. So I'm just going to shrink this. So what a transaction really is these inputs. So there are these addresses that held the coins and we're trying to spend those coins. Okay? And all of these addresses, they were sent these coins in some other transaction that occurred before them. On this UI, you can just click on the left arrow and you can go to the transaction that these addresses received the coins in. And those are the coins being spent right now. And then, apart from the inputs, you have these outputs, which are the receivers of the coins, right? And then you have those instructions of coin spending. So when I send coins to, for example, Shri or Robert, when I send the coins to Shri or Robert, yeah, going through right now. All right. When I spend the coins to Shri or Robert, this is the question I'm posing. Right? I'm saying, apart from other things, I'm saying, check that the signature belongs to this hash. And this hash is the destination address that I was sending it to. It's the public representation. So I'm asking the Bitcoin network, if the signature of the next transaction comes from this address, then he can spend the coins that I'm giving here right now. Right? That is an output script. And there's a lot more you can do with this script. This is a bit complicated. We'll go into this a little bit later. And then you have the input scripts. These are basically signed answers to the previous transaction's output scripts. And they look like gibberish. Am I stepping on something? And that's really what a transaction is for Bitcoin. So now, if anyone asks you, you can go and look it up, and you can look at the input and output scripts. Okay. So I'm just going to plug this in right here. While we wait for this, any questions on what a transaction is and what the structure is and what you can do with it? Yes?
If you make a very complex transaction, like 4 people have to sign it, it can only happen after a certain date, it can only happen within an hour. But again, if you make it very complex, does that mean that that transaction size is small? So the transaction is not just a straightforward, like, send Bitcoin to this address. Like, what's the consequence of that? Is it harder to get it on the blockchain? Is it less likely that
the question is, if I add more data or ask the transaction to do more than I am asking over here, would that change the size of the transaction? What consequences does that have for the transaction? Well, if you ask the transaction to carry more data, which can be instructions or which can just be gibberish data, or it could be a signed document or whatever, there are limitations to what you can add to the transaction. But if you try to exceed those limitations or try to approach those limitations, what you will do is you will increase the size of the transaction. Now, the consequence of increasing the size of the transaction is you have to pay more fee to the miners. Those miners may or may not want that fee or require that fee. But the Bitcoin protocol, if you look at the standard, which is the reference source code, it will ask you to donate 0.0001 Bitcoin for every 1,000 bytes in a transaction. Okay? So if you increase the size of a transaction, you need to pay more fees if you want somewhat of a guarantee that this transaction will be mined. But even then, if the miner is completely ignoring the fees that he has to collect, which is stupid on his part, they may or may not mine the transaction. But in general, and that's a theoretical. In practice, this almost never happens. A miner tries to take transactions that pay him fees. So if you, in conclusion, if you want to raise the amount of information you're putting into a transaction, you pay more fees. Okay? Yes?
In that example, it says number of inputs 34. Like, what exactly 34 means like that? 34 people, there are 34 transactions before that?
So the question is, in the previous transaction that I showed, there are 34 inputs. What is that? I'm telling the transaction to take coins from 34 places and place them into 2 places. So 34 inputs and 2 outputs. Okay? All right. So we went through this, and we went through a live overview using a blockchain explorer as well. Now, I want to wrap this up so we have some brain power left to actually play around with the code. What I want you to do is experiment with the Bitcoin network, and there are really easy ways to do that right now. You can go to any free blockchain API. So for example, you can go to SoChain, which is a pretty full-fledged API, so you can check whether a transaction exists or how many confirmations it has and so on. There's blockchain.info, there's dogechain.info if you want to do it for Dogecoin, there's blocker.io, and all these free APIs exist for you to do exactly this. A point of curiosity, go and try to find whether a given transaction's outputs have been spent before. Just try to do that, just rack your head, try and come up with an answer to this question. If you can answer this question for any given transaction, you have completed the exercise. And I would again like to stress, if you want to know the internals of the Bitcoin protocol, get this book. It's pretty good. It's going to be pretty complicated for you in the beginning, but stick with it. You'll go far. I think that's what I wanted to talk about for now. Yes?
So going back to, if I need to find out how much balance I have, I need to go through all the transactions that I've been involved with.
Yes, let's talk about that offline. So the question was, how do I calculate an accurate balance of transaction? Let's talk about that in a bit. So we'll be here for the coding session and so on. So you can go through that. Yes,
What
Robert?
about another 10 minutes of discussion?
Okay, sure. Yeah. Any questions you guys have? Go ahead.
So does that mean you need to go through all the blockchains too? Yes.
So the question is, do I need to go through all the blocks to make sure the balance that I've calculated for an address
All
is
the way
correct?
back to Genesis.
Typically, no. You don't need to, because if you want to be absolutely sure that the coins that you've collected are exactly the same amount of coins assigned to this address by the blockchain, then yes, you need to go all the way to the Genesis block. So this is something the Bitcoin reference client will try to do. If you load it up on an operating system, it will say 7-8 days to sync the blockchain with the network, right? This is exactly what it's trying to do. It's trying to go back to the beginning of the Bitcoin network, and it is looking at every single block and every single transaction and saying, yeah, you didn't receive any coins in this, you didn't receive any coins in this either. And it keeps going all the way up till now. And every single new transaction that comes in, you check whether any coins are for you and any coins are being spent by you.
So is it fair to, I guess, is it fair to extract that a blockchain that is like a snapshot of the set of transactions at any given point in time, and that keeps getting pulled up?
The question is it fair to say that the blockchain is a snapshot of transactions that occurred at a given time? Loosely, yes. It is not an exact snapshot of transactions that occurred at specific times, because I can send a transaction into the network right now and not pay any fees, and then it takes 2 days for a miners to mine that transaction, because no one wants to mine a transaction that has no fees. So it is loosely a snapshot. Yes, go ahead.
So I heard before in the reference client that it only generates random numbers that go between 2 to 32, and that you should generate your random numbers elsewhere. Is that still true?
No, that is not true. In specific languages, yes, but in general, for the computers that we have right now, for example, I can Let's see what Ruby generates for us. So I can open a so what I'm doing is I'm trying to generate a random number that is between 1 and 2 to the power 256 minus 1. Let's see what it does. It generates a pretty large number. How big is that number? The number of digits in that is 76. So we've got around that problem recently. In some languages that might not be supported, those languages may be outdated, I don't know. But all the languages that we have developed in, I don't think it's an issue. Yes?
What was the general rule of thumb for the increase in transaction size and increased fees that you mentioned?
The Bitcoin reference code. What's that question? The question is, what is the general relationship between the amount of fees I need to pay and the size of the transaction? The general relationship that the Bitcoin reference code wants you to use is 0.0001 Bitcoins for every 1,000 bytes. So for example, if you have 1,500 bytes in a transaction, you will pay twice the amount of the minimum transaction fee, which is 0.0001. So it increments in discrete values from 1,000 bytes, 2,000 bytes, 3,000 bytes, and so on. Yes?
I'm worried about when the block wars have, the Bitcoin network is less secure because the transaction fees may not scale.
The question is, when a block reward halves, is the Bitcoin network less secure when that happens because of network fees? They don't scale. Well, Bitcoin network security comes from the amount of people trying to validate the transactions coming in. So the Bitcoin network security comes in when there are enough miners fighting with each other to validate transactions. There's enough computation power in the network, right? The security of the network basically comes down to is 51% of the network honest. If the majority of the network is honest, which is 51%, they will validate transactions that should be validated, and they will invalidate transactions that should not be validated, right? As long as that happens, the Bitcoin network is secure. The halving doesn't have anything to do with it.
Okay, but after the halving, there's less incentive, unless for miners to, be on a network, right? So.
Yeah, the question is there's less incentive for people to be mining on the network once the reward halves. Yes, this is true, but also we're expecting the value of the coin to go up. So the reward, economics.
Yeah.
Yes.
So if you had 90% of miners instantly just die and go offline, in this situation, would blocks take 100 minutes to validate instead of 10 minutes for the next 2 weeks?
The question is, if all of a sudden most of the miners disappeared off the network and there are maybe 10% of the early miners working to solve blocks, will it take a longer time to calculate the next block? Yes.
The difficulty is dynamic, so it should decrease.
So the comment is, in the Bitcoin network, the difficulty, it scales according to the number of miners on the network. Yes, but that happens once every 2 weeks. So for 2 weeks, you're potentially stuck in a problem where your blocks are taking about 100 minutes or so. That can happen. Yes?
You said that it was quite simple to figure out whether an address was a pre-existing one. Could you just expand on that?
The question is, can you validate whether an address already existed or someone else found it before? You actually don't know that. You know it as long as they have transacted through it. Okay? So I could have a machine sitting in my car calculating different private keys possible on the network, right? Only I know that I found the private keys. No one else does. So if you generate an address that has the same private key as the one calculated by my car, I can just take your coins. You never know until someone actually does transact through that address.
What you want to know is if you created a new one. All you want to know is that it wasn't used before, right?
The question is, all you want to know is whether an address that I created, it was used before or not. The probability of you generating an address that was already used is really small, but it can happen. It's not impossible for that to happen. And again, unless you have transacted with the address before, and if I create the same address again, I will not know that you have the private key to that address. It's just a random integer that I calculated. Okay? So it is really, really important that we use cryptographically secure pseudo-random number generators. We can't just have someone on the street say a random number and that's my private key. They're susceptible to patterns. We're humans, and because of that, that's insecure.